All right, let's talk example 4. So example 4 is similar to example 3 in that we are given the first derivative, but we're given that first derivative in graphical form as opposed to that algebraic form, right? That actually makes things easier. We can, right now, I'm just going to go ahead and be like, knowing what we're doing, I'm just going to go ahead and make a plus minus table. So we have our zeros. I don't have to solve for them. I can see them on the graph. -2, 0, and 1. I can also see what's happening with my graph. It was positive, 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 and we have this one little negative section. Very, very similar to our previous problem. We have 2 zeros that cross, and we have 1 0 that bounces. So we can go ahead and put all that in. So we have plus, we're above, we're above, we're above, and we were below. Right? We could even go back and think about like, well, probably the original function of h prime of x looks something like, ooh, horrible looking x, looks something like x plus 2 has to be even since it bounces. We got an x, and we have an x minus 1, right? So we got all those factors back as the zeros turned back into factors. Now, this is not guaranteed, but they do look pretty linear at those 2 crossing points. It does look pretty parabolic at the bounce, so I'm feeling pretty good. There could, of course, be some sort of multiplier in here as well, but like I said, some version of this, maybe with some a out in front, where a is a constant. That is positive because we need the opening up, but that's beside the point. All right, so let's look at this thing. On what intervals is my h of x, the original function, increasing? Well, we know that's when h prime is positive. So let's go ahead and write those in. Simple enough. It is increasing on negative infinity up until 0, and from 1 to infinity. Oops, I need my hard brackets. Otherwise, I have to include more. Right? If I use the parentheses, that's me saying I don't believe the equal to 0 counts. And so therefore, I would have to do a little bit more work on this to do that. Okay, does h have a local minimum, local maximum, or neither at x is equal to -2? So they're asking us to look at this specific value. And we can see there's no sign change, so it has nothing. There are no local extrema here. Oops, no local extrema or relative extrema because f prime does not change signs. This means that my original function was increasing and then it's still increasing, and so that point where it went from increasing to increasing is nothing special. All right, and then let's see, find an x value where h has a relative minimum. Explain your reasoning. So we know we have two potential candidates here, that 0 and the 1, and we can just think about the 0, we went from positive to negative, that's relative maximum, and at 1 we went from negative to positive, there's my minimum. That's my key here. So we could go ahead and say, okay, h will have, come on, change my pen, maybe it'll let me write again. Will have, nope, I'll type it up. You're killing me, Smalls. All right, h will have a relative minimum at, I also want to make this thing bigger. Whoop. And where's that minimum? Was it x is equal to, played with fire here. There it is. At x is equal to 1, because h prime of x changes signs from negative to positive at x is equal to 1. Cute. There we go. That's example 4. Graph almost makes things easier because I'm using the graph to make the sign table. So if I have the graph, making the sign table is more straightforward in my opinion.